and it's a particular pleasure to reintroduce Jonathan Pila, to add to his biography since yesterday. He's 1 day older, and he has received the Clay Research Award for 2011. He will speak on Diophantine geometry via O minimality.
Okay, thank you for that introduction. So I want to talk about some applications of O minimality to Diophantine geometry. And I guess the talk will have two parts. So the first part will be quite short. I just want to say one or two brief things about the result that I'm going to, the result, the O minimality result I'm going to apply. So that's a result joint with Alex Wilkie about rational points on a definable set. So that's about a kind of analog Diophantine geometry in O minimal structures. And so this was somehow a generalization of this work with Bombieri on rational points on plane curves. And in particular, I want to mention a kind of analog of the idea of the special set in Diophantine geometry. And then the main part of the talk will be the application of that theorem to Diophantine geometry proper. And this was via strategy proposed by Zanya for the Mann-Mumford conjecture. But it turns out that this same strategy has can be applied in several other problems in the circle, the sort of Mann-Mumford, Andre Oort, and indeed the broader, the Silverpink circle of conjectures. And there's various applications that I want to mention. So in Diophantine geometry, there's a general idea that if a Diophantine problem has a lot of solutions, then there must be a geometric reason for this. And maybe the first, the most famous statement along these lines is the Model conjecture, Faultings Theorem, that a projective algebraic curve of genus at least 2 has only, defined over Q, say, has only finitely many rational points, and the same over any number field. If G is 0, then perhaps over some extension field, this curve is P1 and has lots of rational points. And if its genus is 1, then perhaps again over an extension field, it's an elliptic curve, which will, over a suitable field, have infinitely many rational points. And so apart from those geometrical reasons, the number of points is just finite. So Lang somehow considered higher dimensional generalizations of this, in particular to ask the question, when can a projective variety have infinitely many rational points over some number field? And this led him to the notion of the special set. So certainly if this variety contains non-constant images of projective spaces or abelian varieties, then it can have infinitely many points. So he called this special set the Zariski closure of the non-constant images of group varieties into V. And then the conjecture was, so this is a very much open conjecture, that outside the special set, there are only finitely many rational points. And indeed, Faultings Theorem, Faultings went on to prove this in the case of a subvariety or an abelian variety, in which case the special set is some finite union of translates of abelian subvarieties, which of course, if you move the origin, are themselves abelian, they are abelian varieties. So this special set somehow plays a key role. So in 1989, jointly with Bombieri, we proved some results about integer points, but really you can, by the same method, you can prove things about rational points on plane curves. In particular, this theorem here, that on the graph of an analytic non-algebraic function, there are rather few rational points. Now, there could certainly be infinitely many rational points, so this result has to be stated in terms of a height density. You count the number of points up to a certain height, and here we use just this simple height. The height of a rational number in lowest terms will be the maximum of numerator and denominator, and the height of an n-tuple will just be the maximum height of the coordinates. And then somewhat later, Heath-Brown introduced a p-adic version of this method, this determinate method. Somehow this method involves studying certain determinants of the rational points. And his method was applicable to rational points of algebraic varieties in any dimension. So this suggested somehow to look at what could one say about the distribution of rational points on a higher dimensional non-algebraic set. Say, for example, a bounded semi-analytic set, the graph of an analytic function on some bounded region in the plane, or something like this. And in this case, when you have a non-algebraic set, it's now the algebraic subsets of that thing that could cause you a problem and could have many rational points on them. And in particular, they obstruct this determinate method. This determinate method will never prove, I mean, in its simple form at least, that an algebraic variety has less than some positive some t to the delta rational points. So we define this algebraic part of a set to be the union of all connected positive dimensional semi-algebraic subsets. So that's just a definition that you can make. And then the idea is that this algebraic subset is somehow a weak analog of the special set of a variety. And now the idea is that a reasonable set, Z, in Rn, has few rational points outside its algebraic subset. Now, in this context, one can't expect finiteness outside the algebraic part, because sets like the graph of y equals 2 to the x will be perfectly reasonable in this context. And reasonable, the good notion for reasonable is somehow the natural setting for this result is definable in an O-minimal structure. And in that setting, we have this result with Alex, that outside the algebraic part of a definable set, there are at most t to the epsilon rational points. Will define an extension of degree at most k over the rationals, and one can take the absolute height there for the height. And you have exactly the same result, but the constant now, of course, depends on k. So, okay, so just finally, before completing this part, this result cannot be much improved in general, and in particular, you can write down examples where you cannot replace t to the epsilon by a power of logarithm. But Alex conjectured that for sets that are definable using the exponential function, that one can, and there are various partial results in that direction due to Gareth Jones, Margaret Thomas, and Lee Butler in particular, for certain curves and surfaces. Okay, so that's Diophantine geometry in O-minimal structures, and now I want to move to part 2. So this strategy proposed by Zania for a new proof of the Manin-Mumford conjecture, which of course is Raynaud's theorem for abelian varieties over Q bar. So I want to sketch this strategy first for the multiplicative Manin-Mumford. So this is the torsion case of a theorem of Michel-Laurent. But I think it makes some of the points sort of clearer in that example. So this is the problem. So we have an algebraic variety in C star to the n. So V will be defined by some polynomial equations, and we just, from C to the n, we just remove all the points with a 0 coordinate, and that means that our variety is sitting inside a group variety, C star to the n, with coordinate-wise multiplication, and we're going to consider what torsion points of C star to the n lie on V, and these will simply be points whose coordinates are all roots of unity. And so the conjecture, and I put that in inverted commas because that's a theorem of Laurent, that V contains only finitely many torsion points unless there's an obvious reason why that fails. And the reason is that if V contains either a subtorus of positive dimension or a translate of a subtorus by a torsion point, which we'll call a torsion coset. So the subtorus will be a subvariety defined by some multiplicative equations, and its torsion coset will simply be a shift of such equations by a torsion point. And in those cases, the subtorus will have infinitely many torsion points, and they'll all lie in the variety, and so the finiteness fails. But one would like to somehow say that apart from those points, that there are still only finitely many. So you have a refined version where you observe firstly that a torsion point is itself a torsion coset of the trivial subgroup. So you make this refined conjecture, which is also a theorem, that this subvariety V contains finitely many torsion cosets, either individual points or positive dimensional, and they account for all the torsion points in the variety. So if you like, V has finitely many maximal torsion cosets inside it. All right, so now I want to sketch a proof of that theorem using the minimality result. So the first observation is that because torsion points are algebraic, we can assume that V is defined over a number field, or we can simply replace it by a subvariety which contains all its algebraic points. And now we start with the uniformization of C star to the n by C to the n, given by the exponential function. So we simply apply the exponential function to every coordinate. And since we eventually want to talk about sets in an O-minimal structure, we need to put everything inside R to the n, for some, or R to the 2n in this case. So we're going to put real coordinates on Cn. And for that, I'm going to use the real part of each Zi and its imaginary part divided by 2 pi. And this has the result that the pre-images of torsion points, which of course are rational multiples of 2 pi I, become rational points. So we're going to change this problem of torsion points on V to rational points in the pre-image, which of course is some transcendental set defined using the exponential function. Now this uniformization map is periodic, of course, 2 pi I periodic in each variable. So that map is not definable in any O-minimal structure. But if you restrict it to a fundamental domain, to a strip of width 2 pi I and like that, then it is definable in the structure Rn exp. So we need the exponential function on the whole line. And in the imaginary direction, we just need the restricted sine and cosine. So that's all in Rn exp. And so I should remark at this point that people may notice that somehow the torsion points in this case are all on this, they're all on the imaginary axis. So in fact, one can do this whole proof without that big fundamental domain. But in the other cases, one cannot. So when we come to the Manin-Mumford for abelian varieties and the special points in André-Oort, those points are all dense in the fundamental domain. So we don't have this situation. So I'd like to go ahead somehow pretending, if you like, that we need the exponential on that full, well, and we do for another reason. So instead of now counting, rational points, instead of counting torsion points in V, we can now count rational points inside this set Z, which is the pre-image of V intersected with the fundamental, with the Cartesian product of the fundamental domain. And this is a definable set in Rn x. And so we get an upper bound for the rational points. They're at most up to height t. And outside the algebraic part, they're at most t to the epsilon rational points. But on the V side, these points, of course, are algebraic. They're roots of unity. And they have Galois conjugates. And in fact, they have rather a lot of Galois conjugates. A torsion point P of order t has degree phi of t, where phi is the Euler phi function. And in fact, this order is very nearly t, just t divided by a logarithm. So in particular, now, because V is defined over a number field, some fixed proportion of those will lie back on V. So if P contains one such point, if V contains one such point, P, then it will contain, let's say, at least some constant times t to the half such points. And then this will contradict the upper bound. In the upper bound, we can choose epsilon to be a quarter, say, or anything. So these two bounds contradict each other if t is large. And we find that either the order, so now we have to think about that subset. Now, in thinking about the algebraic part of Z, it's nicer to think about the algebraic part of the full inverse image, because that's a complex analytic set. And it turns out that if Z contains real, so in Z, we're looking for positive dimensional, real semi-algebraic positive dimensional things. But it turns out that if Z contains such things, then it contains locally complex algebraic sets. And so what one finds, if you look at the full inverse image, the algebraic part of the pre-image of V is a union of complex algebraic varieties, and we need to understand what they are. So let's consider some irreducible complex algebraic variety W contained in this pre-image, and of course it won't be contained in the definable piece, right? It'll be spread out through through C to the n. And let's consider the coordinate functions Zi bar, the functions induced on W by the coordinates. So these will be some algebraic functions on W. And what this situation is telling us is that the exponentials of those functions now lie in V. They satisfy an algebraic relation. And so we have algebraic functions whose exponentials are algebraically dependent. So this is functional analog of the Lindemann-Weierstrass theorem, which tells us when the exponentials of algebraic numbers can be algebraically dependent. So this functional statement, so Ax in 1971 proved indeed the Shanwell conjecture for the exponential function in a differential field. And in particular, this implies that, using only, so to speak, the Lindemann-Weierstrass, it's the part of Axe-Shanwell that deals only with the Lindemann, with the exponentials of algebraic functions, that if the exponentials of algebraic functions are algebraically dependent, then those functions are linearly dependent over Q modulo constant functions. So I'll write down on the next slide what that means. So by this quite classical theorem of Axe, let me state it here. This is a special case of Axe's theorem, that if you have algebraic functions whose exponentials are algebraically independent over C, then those functions are linearly dependent over Q modulo constant. Some rational linear combination of the functions is a constant. Now, if you think about what that means, it means that W is contained in a translate of a rational hyperplane. But it turns out that this theorem is equivalent to a somewhat stronger version, that if you take the subvariety V, that a maximal complex algebraic variety in the exponential pre-image is in fact a translate of a rational linear subspace. So the algebraic part of the inverse image there is the inverse image of the cosets of subtori. Now here we have not just the torsion. So in the problem we're considering, we only want to see the torsion cosets. That's our exceptional set. But here we have any cosets. However, the non-torsion cosets don't contain any torsion points, and so they somehow don't. They ultimately they play no role. So the algebraic part of Z is almost exactly what it needs to be for the exceptional case in Mann-Mumford. So I just want to summarize briefly and then sketch the conclusion of this argument. So we've got this transcendental uniformization in which the torsion points that we're interested in become rational points, and we have a lower bound from Galois that contradicts an upper bound from Archimedean, from this Diophantine geometry in an O-minimal on a definable set. We have a characterization of the algebraic part using what I call the Axlindemann Weierstrass theorem. And the next thing we need to know is that of the possible subtori that appear here, that have translates that occur in V, that there are only finitely many of them. So I won't go through that. I'll sketch that argument a bit later on in the other situation. But then finally you have an inductive argument that for each of those tori, if you consider which translates of it are contained in V, then that amounts to looking at torsion points in the quotient. So you have a sort of an inductive argument at the end that says that only finitely many torsion cosets of each of those tori are contained in your variety. So let me sketch the same strategy for Mann-Mumford, the original for the, well. So the original Mann-Mumford was about the finiteness that it said that if you had a curve of genus of least 2 and you embed it in its Jacobian, then it only goes through finitely many torsion points. Now, so the Jacobian of the curve is some G-dimensional abelian variety, which is a projective group variety, complex analytically isomorphic to the C to the G modulo a lattice. And in the lattice, so this is a fundamental domain for the lattice, with the black dots indicating the torsion points. So there you can see the division points of the lattice, and there you can see that they're becoming dense as you draw more dots. So that when you embed, J, of course, is the Jacobian, is an algebraic variety, but the torsion points are still dense, somehow when you embed the curve, it manages to avoid this orbit a finite number of this countable dense set of points. So this, that original statement was also extended by Lang to subvariety of an abelian variety, that V has only finitely many torsion points unless it contains a translate of an abelian subvariety. And then there's, of course, there's a refined version that I think is on the next slide. And this was all proved by Raynaud in 1984. In the meantime, Lang had showed how this was somehow you could connect this with the Mordell's conjecture, and one had the Mordell-Lang, which was then proved by Faultings and various other people. But I only want to talk about torsion points. So here it is again. We have an abelian variety which is complex analytically isomorphic to Cn modulo a lattice. Torsion cosets will be translates of an abelian subvariety by a torsion point, and we have this refined statement. For a subvariety, there are only finitely many torsion cosets contained in V that contain all the torsion points. And this has several proofs after starting with Raynaud, but there are many proofs of this result, including a proof using model theory by Hrushevsky. But it's quite a different kind of model theory to this proof. So the proof, okay, here's a sketch of the proof, which looks exactly the same. We start with the uniformization of the abelian variety by Cn, given by some theta functions. And they will be functions, periodic or nearly periodic modulo the lattice. I mean, the map will be periodic modulo the lattice. And then we put real coordinates on C to the G, or C to the N, I guess, using a basis of the lattice. And in that basis, the torsion points are exactly the rational points. And now this map theta is given by some real analytic functions. So now we have real analytic functions on the fundamental domain is a compact bounded domain. So this will be definable in Rn. And we can go through exactly the same thing. We take the pre-image of our subvariety V. We intersect with the fundamental domain. We call that set Z. And we go looking for rational points. And we have an upper bound. And on the other hand side, again, we have a lower bound coming from Galois. So this is a particular result of Massa. I think there are various, this result has been refined in various ways in the meantime. But torsion points have high degree. And if you fix your abelian variety, then there's a constant C of A. The degree of P is at least some positive power T to the delta of its order. And here delta, in fact, only depends on the dimension of the variety, although that doesn't really matter here. So the upper bound contradicts the lower bound, since we can choose epsilon to be less than delta. And now again, one needs the Axlindemann-Weierstrass statement, which is again a part of an Ax-Chanwell result that you can take. There's a version of this due to Ax, and there are more refined versions due to Kirby. And in fact, in the paper with Zanya, we hadn't completely made the Ax-Chanwell connection, so we actually reproofed that theorem using O minimality. And one has a similar inductive conclusion. So I guess now I want to talk about the André-Oort conjecture. So this is an analog of Manin-Mumford conjecture for Shimura varieties, which I'll denote X. So examples of Shimura varieties are moduli spaces of principally polarized abelian varieties of a given dimension, things like Hilbert modular surfaces or Hilbert modular varieties, modular curves, Shimura curves, things like that. And in a Shimura variety, you have a notion of a special point, which I'm only going to define in the particular case I want to talk about, and special subvarieties. And you have this conjecture, Andre-Oort conjecture, that if you take a subvariety V of a Shimura variety X, then V contains only finitely many special points unless it contains a special subvariety of positive dimension. And the special subvarieties do indeed contain infinitely many special points. So this is sort of a sharp statement. And you have a refined version, again, that in fact all of the special points in your variety are accounted for by finitely many special subvarieties. Okay, so this in general, this proof of this theorem in general has been given in work of Klingler, Ulmo, and Yafeev on assuming the generalized Riemann hypothesis for imaginary quadratic fields. And rather few cases are known unconditionally. So what I want to sketch, I guess, well, I want to first describe the Andre-Oort conjecture for Cn a little bit more precisely, and then sketch an unconditional proof of it using O minimality. So this case is the Andre-Oort conjecture for C to the n. So C here is the modular curve. It's the J line parametrizing elliptic curves by their J invariant. So if you have an elliptic curve, that will be complex numbers modulo a lattice, and you can write that lattice, change that lattice to be in the form z plus z tau, where tau is in the upper half plane. So J of tau is then the J invariant of that elliptic curve. So this is a function, analytic function on the upper half plane onto the complex numbers, and it is invariant under SL2Z, acting as Mobius transformations. The special points in C are the J invariants of elliptic curves with complex multiplication. So they're curves that have more than the usual endomorphisms. And in Cn, a special point is an n-tuple of such points. So it's the J invariance of, it's a tuple of J invariants of Cm elliptic curves. And in this case, the Andre-Oort conjecture says the subvariety of Cn has only finitely many special points unless it contains a special subvariety, positive dimension. And those are, I'll describe them a little bit more fully in the course of the proof. They are essentially products of modular curves. Modular curves will have infinitely many special points because if one of the points, if one of the coordinates has Cm, then the isogenous elliptic curve will have Cm as well. So they somehow preserve the special points. So for Cn, the Andre-Oort conjecture was proved by Edixhoven under GRH for Cm fields. But for n equals 2, it's an unconditional theorem of Andre. So I want to sketch now the proof of this theorem, unconditional proof. And this will be a reprise of the previous proofs, in particular the multiplicative Munn in Mumford. But we're just going to replace the exponential function by the J function somehow. And we do the same proof. So we start with the uniformization of C to the n by H to the n, just evaluating the J function on each coordinate. So this function will be SL2Z invariant in each variable. And the special points, J of tau is special exactly when tau is imaginary quadratic in the upper half plane. So that's a point of a bounded degree, the quadratic point, even in real coordinates. So here I'm going to take the real and imaginary parts, and then these taus will be quadratic points. And on the other hand, on the J side, one knows the degree of the extension of Qj of tau over Q is the class number of the corresponding discriminant. So that's all completely classical. So now we need our opposing bounds. Now, so J is definable in this fundamental domain. Did I draw the fundamental domain? Yeah. So that's the fundamental domain there. Standard fundamental domain. The J function is definable there, even though it has a essential singularity in the cusp. So it's not definable in Rn, but it actually looks like the exponential function as you go up into the cusp. And it is definable in Rn exp. Now, that is actually, you can see that in Rn. But in fact, it was observed, and it follows from a more general result of Peterzil and Starchenko about the definability of the Weierstrass P function as a function of both the z and tau variables. So again, we're going to, z here will be the pre-image under the J function of our variety V intersected with the fundamental domain. And in that set Z, we're going to go counting algebraic points of degree 2. And we have this upper bound outside the algebraic part. There are only t to the epsilon points. On the other hand, we have a lower bound, which is a classical theorem of Siegel. Well, the degree of the special point is equal to the class number. And the class number is at least t to the half minus any positive eta. So here, this result is unconditional, although it is ineffective. One doesn't know how to work out what that constant is. But it is an unconditional result. And so now we're going to compare the upper and lower bounds. I mean, the lower bound is on the discriminant, and the upper bound is on the height. But in fact, if you take a particular discriminant, the corresponding tau in the fundamental domain is very easily seen to have height that's bounded by the discriminant. I guess I should have absolute values on that, on some of the d's. So you get a lower bound, and these are incompatible bounds. So you again have the situation that either the number of points, special points, is finite, or this set Z, the algebraic part, is non-empty. So all of this somehow, when you come to look at this problem, all of this was basically sitting there in the literature. And somehow the last thing that one needed to prove was the corresponding Ax theorem, what I call Axlindemann-Weierstrass for the J function. So this was not known in this case. So if G now is a 2x2 rational matrix with positive determinant, then the two functions J of tau and J of G tau, acting as fractional linear transformation, are algebraically dependent. So that's the bimodular relation. So one needs to know essentially that the modular relations are the only relations between the J functions of algebraic functions. So let me say precisely what one needs. If I have a W, W is a variety in C to the n, let's say, which intersects the upper half plane to the n. It's in a non-empty set. And if I have algebraic functions that are in the function field, I will call them geodesically independent if they are non-constant and there are no relations between them of the form AI equals GAJ, where G is in GL2Q+. There are no modular relations between those functions. And then the Axlindemann-Weierstrass theorem says that if they're independent in that sense, then the J functions of them are algebraically independent functions over C. And so I want to state an equivalent version of that. So I'll call up in the upper half plane, the pre-images of special subvarieties, well, will be described like this. So we have this notion of a weakly special subvariety in h to the n, and that will be W intersect h to the n, where W is a subvariety defined by these kinds of equations. Some coordinate is G times another coordinate, where G is in GL2Q plus, or some coordinate is constant. They define our weakly special subvarieties. And the special ones, if the CKs are quadratic, if they're special points, then that's a special subvariety. And the images of such things are the special subvarieties in C to the n. Now, a data like that, if I forget about the ones that are constant, I get this, what I call this W subscript with the IKs, the JKs, and the GKs. So that's on some subset of the coordinates, and that now has only the GL2Q relations. And I'll refer to the weakly special subvariety as being a translate of that W sub curly bracket stuff by the various fixed coordinates. So the weakly special things come in these families, and inside those families, the special subvarieties are the ones corresponding to translations by special points. So these are like cosets, torsion cosets. And then the theorem, the equivalent Axlindemann-Weierstrass theorem, is that if you take V, subvariety of C to the n, you take its inverse image under the J function, a maximal complex algebraic variety in there is weakly special. That's what we need. So I want to sketch the proof of that a little bit, which uses O minimality and my result with Alex a second time. So we take this definable set Z to be the intersection with the fundamental domain as usual, and we suppose that W is a maximal algebraic subvariety which intersects Z. Then we can operate on that by SL2Z, by the periodicity. Any SL2Z to the n translate of W will also be contained in the inverse image. And I can look in particular at the G's that intersect Z in the full dimension. Now, of course, I can't ask for the G's in SL2Z that do that definably. SL2Z is not a definable subset, but SL2R is a definable set. It's because it's a semi-algebraic set. So I look at the G's in SL2R to the n for which GW intersects my definable set Z in its full dimension, the full dimension of W. And for all of the G's, such G's, GW will actually be contained in the inverse image of V by analytic continuation. But that set of G's is a definable set. And also, it has many integer points because it has a lot of SL2Z points in it. And so by my theorem with Alex, it contains a positive dimensional semi-algebraic set. But that gives me essentially a deformation of this W, which is entirely contained inside the preimage of V. And you can complexify it. It's a real one, but you can complexify it. And if that deformation moves W, then it will give you a set of larger dimension. But we said W was maximal, so this family must somehow translate W along itself. It stabilizes W. And well, this is somehow you can play this game in a lot more detail, and you generate identities. So you take your W to be defined by certain functions, and you prove that these functions satisfy identities like this. Phi of GZ is equal to H of phi Z, where G and H are in SL2Z. And you generate a lot of identities like this, and that eventually forces phi to be in GL2Q+. So there's quite a detailed game that goes on there. But so there's a second use of O minimality here, and I just want to somehow say that in the first, the opposing bounds takes place within the fundamental domain. One uses the definability in here and of this set Z and the special points, whereas in the second use, we're looking outward at the ambient space, which is the upper half plane, or SL2R to the n, and in there, SL2Z is playing the role of integer or rational points. And in this second part, also the Axlindemann Weierstrass, one doesn't need lower bounds. Somehow these sets, SL, one knows how many SL2Z points there are. So now we need a finiteness statement that these W's, that the only finitely many of these W's with relations on some of the variables have a translate that occur as a maximal algebraic subvariety in the pre-image. And here, it's again a proof using O minimality. The set of W's, we can look at the set of W's that arise in that way with the G's in SL2R. With the G's in SL2R, that becomes a definable set. Which G's have the property that that W has a translate that intersects Z and is maximal among such things? That's a definable set. But we've proved that everything in that set is a rational point. So the G's are all in GL2Q. So now we have a definable set whose every point is rational. And that set has to be a finite set. Otherwise, if it were infinite, it would contain something continuous. So this is a third use of O minimality in this argument. And now I maybe should not dwell on this part, but we have the conclusion. We can define the special subset of V to be the union of positive dimensional special subvarieties in it. The first proposition is that André Oort holds if that special subvariety is a variety, if it's a finite union, because you just play the same game with opposing bounds. There can only be finite order of discriminant of point that doesn't lie in there. And then you prove inductively that the special subvariety is a variety by going to the quotient and looking at the special translates like that. So there's this inductive scheme. So this same strategy, similar strategy, if you're using O minimality, has been used in several other contexts. So I want to talk, hopefully, a bit later about Masazania and anyhow some results in the Silverpink area. But in terms of other cases of André Oort or generalized versions, Dor, Yafeyev have given an unconditional proof of André Oort for Hilbert modular surfaces using this technology. Also, one can prove generalized versions where you take Cn, cross a bunch of elliptic curves, cross a bunch of copies of GM, and you can prove somehow the generalized André Oort there. And other results somehow in progress for products of elliptic modular surfaces and so on. In particular, with Jacob Zimmermann, we are in progress of proving André Oort for the Siegel space of two-dimensional abelian varieties. And you can also prove some other algebraic independence results along these lines. So what somehow are the ingredients that you need? Of course, every Shimura variety looks like has some kind of transcendental uniformization, which is invariant by some discrete subgroup. So what do you need? Well, for the opposing bounds, you need a definability of the uniformizing maps. So Petersil and Starchenko have established that for theta functions in both sets of variables. So one now has definability for the AG, for the principally polarized abelian varieties in any dimension. The lower bound on Galois orbits are not available in general, but very recently Zimmermann has them for AG up to at least G equals 5 or possibly 6 unconditional lower bounds. There are some similar results along those lines of Yafeyev and Ulmo. And then the other ingredient you need is this Axlindemann-Weierstrass statement. The maximal algebraic W in a pre-image is weakly special, which again is not known in general, but on the other hand is approachable without lower bounds. You don't need lower bounds to think about that. So, okay, in the last little bit, I want to talk about the Silverpink conjecture. So the Silverpink conjecture is a far-reaching generalization of Andre Oort and Mann and Mumford, and it was framed independently first by Silber in the semi-abelian context, most generally somehow by Pink to include Andre Oort, and in the meantime by Bombieri Masazania, who were working on what they called unlikely intersections in C star to the n. So Silber was coming from a model theory. He was studying the model theory of exponentiation. So here the sort of the guiding conjecture is the Shanwell conjecture, and somehow his what he called the CIT, conjectures on intersections with tori, somehow came out of his thinking about that. Pink, it seems, was trying to unify Andre Oort and Mann and Mumford and make them part of the same statement. So here is somehow the simplest version. So we'll take, in C star to the n, we'll let S square bracket k be the union of all algebraic subgroups of codimension at least k. So that's some countable union of subvarieties. So if you have a curve inside C star to the n, then generically you would expect it not to intersect anything of codimension 2 or more. So the conjecture says that if you intersect a curve, so the conjecture says in general that unlikely intersections that are unlikely by virtue of dimension are somehow indeed very unlikely to occur. So in the case of a curve, it would say if you intersect a curve in Gm to the n, in C star to the n, with algebraic subgroups of codimension at least 2, that gives you only a finite set of points, unless there's an exceptional case in which your curve is indeed contained in a proper algebraic subgroup. So that's a theorem. That conjecture is a theorem of Bombieri, Masazania, and Morin. So what are the points in that intersection? They are the points x1 up to xn where there are 2 or more independent multiplicative relations on the coordinates. So of course that's much stronger than the Mann and Mumford problem where you look for n independent multiplicative relations on the coordinates, or if you like, n equals 2. And the Silberpink conjecture implies Mordell-Lang. So I just want to sketch that for curves. If you have a curve in C to the n, you can imagine that this curve has all but 2 coordinates constant. So your curve looks like C1 up to C coordinates. And then if you have 2 equations, 2 multiplicative equations, it amounts to solving f of xy equals 0 in the division group of the C's, which is the Mordell-Lang problem in that case. So although Silberpink only involves special points and special subvarieties, it implies Mordell-Lang as a kind of degenerate case. So I guess I just want to sketch very, very briefly a result with Habegger. So, of course, as part of Pink's conjecture, you get similar conjectures in the Shimura variety. So you can look for a curve in Cn as a Shimura variety and intersect it with the union of special subvarieties of codimension at least 2. And then the conjecture says that that's a finite set unless C is contained in a special subvariety. That's a special case of Pink's conjecture. And so using the same technology, we can prove that, unfortunately, under a rather special condition. So C has to be defined over Q bar, and it has to have this asymmetry condition. But it's the same strategy, and now the X result you need is for the logarithm. You need to know that the inverse J function of algebraic functions are algebraically independent. It's, so to speak, the X logarithms of the J function. And you get, so maybe I'll really finish with that, is that, of course, this again implies something that you can consider to be a Mordell-Lang problem in the Shimura variety. If the curve has fixed coordinates, then you're looking for points on the curve fxy equals 0, where x and y are in the Hecker orbit of the fixed coordinates. So that's kind of analog of Mordell-Lang. And that problem we can prove in general. So for any subvariety of Cn, maybe I won't go through all of that. But so that statement you can consider as the Mordell-Lang for Cn. So then there was some sketch of that. I wanted to mention briefly the Masazania result on torsion anomalous points. So this is a version of Mann and Mumford. I won't go through it, but you have a curve in a family of abelian varieties. And the point here is that the abelian variety is different at every point. It's a curve in a moving family, but you have the same statement. This is a rather special case. They can do more general cases now. But just so to finish with the idea that apart from more, of course, one can try to prove more cases of Angers or Silverpink and so on. One can also ask various definability questions about transcendental maps uniformizing quasi-projective varieties, or if you like, the inverses, the hypergeometric functions, to what extent you can find them in an O-minimal structure. This kind of approach, for the moment, can't seem to touch problems like the Mordell problem itself because there are no Galois conjugates, but it's a question whether there's some kind of O-minimal angle there, or perhaps other questions. Anyway, so O-minimality is a new tool in Diophantine problems, which seems to have interesting prospects. Okay, thank you very much.
Well, thank you for that fascinating introduction to O-minimality, and welcome to the logicians to the world of number theory. Welcome again. Glad we'll hope this will be a precursor of many more meetings, joint meetings with logicians and number theorists. Do you have any questions for John?
So can you just elaborate a bit the last remark on Mordell's conjecture? I mean, what are the obstacles to replacing torsion points by a subgroup, a finitely generated subgroup of an abelian variety?
Oh, well, the obstacle is simply that there's no Galois action on the rational points, so the lower bound goes away.
What I mean is, are there any prospects for attacking that case without the Galois action?
No. But one should think about it. I mean, if you believe that Mordell-Lang is one conjecture, then somehow maybe there should be an approach to the other part of it. But whether the Mordell seems to be a problem in Diophantine approximation, and whether there's an O-minimal angle there is unclear. But yeah, this strategy just goes away because you lose the lower bound.
Just to clarify the ineffectiveness, so the only place where it's ineffective is in the use of Siegel. Right?
Yes.
So that means that if you're given a subvariety which contains no of the Shimura variety, or whichever case you're dealing with, then you would not be able to actually determine all the points on it by this method.
That's right.
If it was supposed, you
That's true. I think people have done it now effectively in C2.
In the multiplicative case, it's effective.
It's effective. No, I mean the Shimura. I mean the modular case. But also there are these results that say there's at most one exception. So you can
Right, I understand.
you never know where it is, but so you can effectively, well, right.
Well, unless you find all of the ones, then, which you'll never find. Yeah.
Right.
So that while you avoided the use of the GRH, it's the ineffectiveness remains. Yeah.
Yes, that's true.
Okay, let's thank the speaker again.
I'd like to say just, hold on just one sec, folks. I'd just like to use this opportunity to thank one group of people and several individuals. First of all, the Scientific Advisory Board, because the choice and the quality of these talks is entirely their doing. So thank you very much to all the members of the SAB. And then I would like to thank Alaji Patel for all of the organizational work that went into this conference, because that is entirely her doing. So thanks, Alaji.